This is SpaceTime Series 28, Episode 21, for broadcast on the 17th of February 2025. Coming up on SpaceTime, new research suggests the Earth's inner core could be far less solid than previously thought. China's new Lunar South Pole mission designed to search for water ice. And the hot Jupiter exoplanet that could provide new insights into how these bodies form. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study has found that the Earth's inner core is undergoing structural transformation and may in fact be far less solid than previously thought. Planet Earth's core consists of a molten metallic outer layer surrounding what was thought to be a spherical solid, mostly iron-nickel alloy inner core with a radius of about 1,220 kilometres, making it about 20% of the entire planet, and with a temperature of around 5,430 degrees Celsius. The characteristics of the core have been deduced mostly from measurements of seismic waves in the Earth's magnetic field. But now a report in the journal Nature Geoscience suggests that the surface of the inner core may be changing. The study's lead author, John Vidal from Dornsife College, says changes to the inner core have long been the topic of debate among scientists. However, most of the research has been focused on assessing the core's rotation. What Vidal and colleagues ended up discovering is evidence that the near surface of the inner core undergoes structural change. The findings shed new light on the role that topographical activity plays in the rotational changes in the inner core, changes that have minutely altered the length of the day and may relate to the ongoing slowing of the inner core's rotation. The original aim of the research was to further chart that slowing of the inner core's rotation. But as they analysed multiple decades of seismographs, one data set of seismic waves curiously stood out from the rest. Vidal says he realised he was staring at evidence that the inner core wasn't solid. The study utilised seismic waveform data, including 121 repeating earthquakes from 42 locations near Antarctica's South Sandwich Islands, which occurred between 1991 and 2024, providing a glimpse of what takes place in the inner core. As the authors analysed the waveforms from receiver array stations located near Fairbanks in Alaska and Yellowknife in Canada, one set of seismic waves from the latter station included uncharacteristic properties which the team had never seen before. At first, the dataset confounded Vidal, but once his research team were able to improve the resolution of the data, it became clear that these seismic waveforms represented additional physical activity in the inner core. And this physical activity can best be explained as temporal changes in the shape of the inner core. The new study suggests that the near surface of the inner core may be undergoing viscous deformation, in other words, changing its shape and shifting at the inner core's shallow boundary. Now, the clearest cause of this structural change would be interaction between the inner and outer cores. The molten outer core is widely known to be highly turbulent, but this turbulence hasn't been known to disrupt the inner core, at least not on human timescales, until now. Vidal says what we're observing in this study for the first time is likely the outer core disturbing the inner core. This discovery is opening a new door, revealing previously hidden dynamics deep within the Earth's core, and it will lead to a better understanding of the Earth's thermal and magnetic field. This is SpaceTime. Still to come, China's new Lunar South Pole mission Chang'e 7, which will do a surface search for water ice, and the hot Jupiter exoplanet that could provide new insights into how these bodies form. All that and more still to come on SpaceTime. Beijing's issued a new press release saying it's on track to launch its Chang'e 7 mission next year to search for water ice deposits at the Lunar South Pole. And once they're identified, mission managers will trial new technologies designed to help taikonauts extend manned operations on the lunar surface. Chang'e 7 will include a new type of molecular analyzer, specifically designed to verify the presence and extent of water ice in South Pole craters whose floors are in permanent shadow, never receiving sunlight. While Beijing's earlier Chang'e 3 and 5 missions landed on the lunar near side, Chang'e's 4 and 6 both touched down on the lunar far side. Chang'e 7 will build on that success, uncovering usable lunar water ice, which can then be broken down and used to make rocket fuel, water for drinking and air for breathing. This would dramatically lower costs, reducing the logistics needed to establish a permanent base on the lunar surface and support future manned missions to the Moon, Mars and beyond. Beijing says China plans to land taikonauts on the lunar surface before 2030 and shortly afterwards commence construction with the Russians of a joint base. Next year's Chang'e 7 mission will consist of an orbiter, a lander, a rover and a mobile hopper designed to jump from sunlit areas to shadowed craters using a new type of active suspension system. As well as gathering data about its surroundings, the mission will also use a landmark image navigation system in order to determine its location, something NASA's been doing for a while, but which will be new for China. This is SpaceTime. Still to come, the hot Jupiter exoplanet that could provide new insights into how these bodies form. And later in the science report, the World Meteorological Organization has now confirmed that 2024 was the first year where average global temperatures were greater than the 1.5 degrees above pre-industrial levels specified by the Paris Agreements. All that and more still to come on SpaceTime. When you study astronomy at university, you quickly become proficient in classical mechanics and Keplerian orbits. They allow you to accurately predict the motions of two bodies, say planets or a planet and a star, based on their masses, velocities and distances. Trouble is, astronomy's not always that simple. In the real world, other bodies and their added gravitational influences add additional complexity to these problems, and this is the basis of the three-body problem. Once you add a third variable in physics, you need to take into account the initial positions and velocities, that is momenta, of all 3 point masses that orbit each other in space, and then calculate their subsequent trajectories using Newton's law of motion and universal gravitation. But unlike the two-body problem, which uses a very simple equation, the three-body problem has no general closed-form solution. You see, when three bodies orbit each other, the resulting dynamical system is chaotic for most initial conditions. Now, astronomers have found an unexpected three-body problem in the discovery of a hot Jupiter's eccentric orbit. The authors were analysing data from a newly discovered massive planet on an extreme orbit in order to understand how hot Jupiter planets form. The discovery of this strangely acting exoplanet 1,100 light-years away has helped astronomers better understand the formation of a class of planets known as hot Jupiters. These are gas giants orbiting close to their host stars. The new discovery, known as TIC 24-124-9530b, is a gas giant about 5 times the size of Jupiter. It was discovered by NASA's TESS, that's the Transiting Exoplanet Survey Satellite, a space telescope gathering information about exoplanets, that is, planets orbiting stars other than the Sun. So far, over 5,000 exoplanets have been found, and many others are suspected but not yet confirmed. That's part of what TESS is doing. Macquarie University astronomers Dr. Jamie Alvarado Montez and Associate Professor Christian Schwab were among a team of 60 researchers from 8 countries and more than 35 institutions studying this fascinating system. Their findings, reported in the journal Nature, showed that the exoplanet's strange orbit indicates that it's under the influence of a second star, indicating a binary system. Now, binary systems aren't that uncommon. In fact, most stellar systems in the Milky Way are multiple star systems. Even our nearest stellar neighbour, Alpha Centauri, is actually a triple star system. Schwab designed the optics for NASA's Extreme Precession Radio Velocity Spectrograph, a crucial part of the ground-based equipment used to home in on the target planet, after TESS first spotted an indication that a planet could be orbiting the star TIC 24-124-9530. The spectrometer was fitted to the 3.5-metre WIN telescope, making over 50 high-precision observations spanning some 2.5 years. Schwab says the observations measured the planet's mass and revealed its extreme orbit. Based on this work, he was able to determine that TIC 24-124-9530b experiences radical temperature changes during the 6 months it takes to orbit its main host star. When closest to the star, the planet's atmosphere would expand and partially evaporate from the intense heat and radiation, and the side of the planet facing the star would be hot enough to melt rock or vaporize metals. But as the planet orbits away from the star, it would cool dramatically, as the constant heating and cooling cycles create powerful storm systems far more extreme than anything seen on Jupiter, and certainly heaps more than anything seen on the Earth. Once the orbital parameters were precisely known, Alvarado Montes got to work on computer modelling, simulating how the planet's orbit would change over time. The models suggest that this planet did initially form as a cold Jupiter far from its host star. But the influence of gravity from that star and from the star's binary partner caused it to gradually migrate inwards and eventually become a hot Jupiter. Alvarado Montes says that several billion years ago, the planet formed as a cold Jupiter, far from its star in a region cold enough to condense and take shape. Then gravitational forces from the second binary star in the system caused the planet's orbit to gradually stretch and grow more eccentric, and it began to swing ever closer to the primary star. The authors have dubbed this newly discovered planet a hot Jupiter progenitor and have modelled the exoplanet's slow evolution to its current highly eccentric 166 Earth-day orbit. From very close to its host star, 10 times closer than Mercury is to the Sun, the planet moves in an egg-shaped orbit, swinging further out to about as far as Earth is from the Sun. Few exoplanets have orbits this extreme. In fact, it's more eccentric than any other known transiting exoplanet. Hot Jupiters are fascinating because they challenge our understanding of planetary formation and evolution. In fact, the very first exoplanet ever discovered, 51 Pegasi, was a hot Jupiter. Alvarado Montes says that in our own solar system, Mercury is a tiny rocky marble orbiting the Sun every 88 Earth days, while the gas giant Jupiter, the king of planets in our solar system, takes around 12 Earth years to complete each orbit. Now, by contrast, hot Jupiters are gas planets like Jupiter or even bigger, but so close to their host stars, their orbits can take less than 10 Earth days, sometimes just a matter of hours. Now, theoretically, these planets should only be able to form at very far distances from a star. That's because the gas making up more than 90% of their mass shouldn't be able to accumulate or survive close to the star's intense heat and radiation. Typically, as planets form close to young stars and grow from tiny clouds of dust and gas, a star's heat causes gas particles to evaporate or condense so that only rocks and metal remain. NASA's Galileo probe, which gathered data about Jupiter back in 1995, transmitted for an hour and reached a depth of about 160 kilometres below the cloud tops before the planet's mounting atmospheric pressure crushed it out of existence. Although Jupiter could fit 1,000 Earths within its atmosphere, it only has a tiny core about the size of the Earth's core, and that's buried under some 70,000 kilometres of gas. That results in pressures millions of times greater than what we see here on Earth's surface. This newly discovered exoplanet sheds light on the formation of hot Jupiters and provides a real-world example of the mathematical puzzle of the three-body problem. The authors have modelled the history and likely progression of this planet, and they predict a happy ending. Alvarado Montes says that over the next million years or so, the planet's likely to settle into a more stable close orbit around its primary star and fully transform into a hot Jupiter.
The first data that we work on to confirm this planet was taken in 2020. So the initial data was data taken by the TESS satellite. It's a mission from NASA to observe exoplanets. Before that, we had Kepler that only observed very far stars, but now we have TESS, which is observing kind of like the nearby universe. What it does is just measure the change in the brightness of the star.
All right. So
and detecting the transits using, the transit method. And then based on that, depending on what you observe, then you do follow-up observations with ground-based instruments or telescopes. So it's a planet that has a very large orbit. So it's a planet that has an orbit of, then observing with TESS continuously is not possible. It's very hard because TESS only observes one sector. So the way TESS observes is observing sectors of the sky, and each sector it observes it only for 27 days. So that means that in the case of this planet, observing it with TESS is very complicated because to get to the same sector it will take almost a year or 2 years, right, to get back to the same sector. So we need to do follow-up observations. So the first observations were done with TESS, but then after a transit was detected, like a transit signal was detected, then the goal was to observe more transit. So the initial data that we have the ephemeris of this planet were a bit complicated. They weren't very well constrained. So that means that some of the attempts that we did with ground-based telescopes were unsuccessful because we were observing supposedly the transit, but no transit was coming up in the observations, just because we didn't have enough information to know with very good precision at what time the observations were like the transit was going to happen. So it took a couple of attempts until like we refined the ephemeris of the planet. And then once the ephemeris of the planet were refined, then we were able to do more transit observations. And also we did ground-based observations with instruments that are called spectrographs. And that's where Chris comes into play, because Chris is the main investigator and one of the people who designed and built the NUID spectrograph. So the NUID spectrograph is an instrument that is located in the States. Like a big bunch of the observations, like a lot of the data that was collected to do follow-up observations were taken with this instrument, with NUID. What we did was observing now not just transits, but we also did observe the radial velocities, the wobbling of the planet. So all of these combining photometric observations, then we were able to constrain the size of the planet, not just constrain like the radius of the planet, but also the mass of the planet. And there is something that you can get. There is a piece of information that is actually quite valuable, and that is only possible to obtain once you observe transit and radial velocities at the same time. So that's what we did with NUID and with other telescopes. So by observing the transits and the radial velocities, the wobbling, at the same time, you're able to recover something that is called the projected obliquity of the orbit of the planet. So this is how inclined the orbit is with the equator of the star. So this is an important piece of information because it can tell you a lot about the history of the planet, like how the planet was formed. So by doing all of these observations, and the name of this method, the name of this combination of photometric data and spectroscopic data, that combination is called the Rossiter-McLaughlin effect. And that's something that we did with NUID, with the instrument that Chris built.
How do you know where the equator of the star is? Are you looking at the star as it's rotating? Is that what's letting you see the different areas of the star? Different
basically. Yeah, very good. Yeah, it has to do with like how the star rotates. So if like the stars are rotating, so the equator is defined by the axis of the rotation. And basically, because these are very big bodies, then what you observe is that when the star is rotating, one side of the star is coming towards you and the other side is going away from you. And so the side that is coming towards you, that is getting closer, that's a blue shift, and the other side is a red shift. So if you are able to measure this shift, this is called the Doppler effect. So that's kind of like an optical Doppler effect. So you're able to observe that optical Doppler effect while the planet is moving in front of the star. Then you are able to tell like how the planet is orbiting around the star. If it's doing it in an aligned orbit, or an orbit with 20 degrees, or with 40, or with 50. So that's what we call the projected obliquity. It's like with respect to the star in the background, the planet passing in front of the star, and you observing from Earth, how is the planet passing in front? Is it passing through a horizontal line, completely flat, or is it moving a little bit with an inclination? So that's what we observe with this effect.
If it's moving horizontally with the rotation of the star, that would tell you that it was formed in a planetary nebula when the star was
Exactly.
formed.
Very good.
At an angle, what does that tell you?
So if it's moving at an angle, then different things, there's different reasons for it. But one of the best theories we have is called a high eccentricity tidal migration. So basically, when you find that planets are, like you said, aligned with the orbit, these are planets that probably like migrated with the disk. So this is called disk migration, what you described before, with the planetary nebula of the disk. But when you find that there is an obliquity, then you have a planet that didn't migrate through disk migration, but a planet that instead was excited by the presence of other bodies in the system. And that is one of the reasons why this planet is so important, because so far we only have one planet that was kind of like a potential member of this sample, that is HD A0606b. So this planet has a very high eccentricity too, like 0.93, has a very high mass, and was the only one. We didn't have any other planet in this sample. So what now with this planet, we have added an extra point in the sample showing that there is a trend between the mass of the planets and the eccentricity of the planet. So what we have found before is that low mass planets tend to be in like roughly circular orbits or orbits with very small eccentricity, while massive planets like HD80606b, or the one that we just found, that are high eccentricity planets, that are also very massive planets. And what happens is that this also proves another thing, or it can help us study another effect of why this is happening. Like why is this dearth of planets with low orbits, with a small orbit, but that are not migrating or becoming hot Jupiters? Because at the end of the day, that was the whole point of this investigation, of this research, right? That these planets that are undergoing this high eccentricity tidal migration will eventually become hot Jupiters. Why? Because they are in such eccentric orbit that when they pass through the periastron, which is the closest point in the orbit of a planet to the star, when they pass through the periastron, a lot of energy is lost. This orbital energy is stolen by the star. So what happens is that with time, then the planet will start precessing and the orbit or the semi-major axis of the planet will shrink. So reaching final orbits of only 10 days or less than that, which is the definition for hot Jupiter. So that's why the title of this paper is called like a progenitor, a hot Jupiter progenitor, because it's a planet that will become a hot Jupiter eventually. Now, we know about hot Jupiters, and we have a lot of information about them.
Well,
but
Pegasi 51 is the best example, isn't it?
Yeah. But the problem is that so far we didn't have a lot of evidence for this mechanism, for the mechanism that I just described, the high eccentricity tidal migration. We didn't have enough evidence because the evidence for this mechanism is precisely that. You need like very massive planets with very high eccentricities, and then observing these planets well enough and long enough so you can constrain their ephemeris, and then eventually knowing what's going to happen with this planet. So the prediction that we have with this planet is that this is a planet that started in a very, very eccentric orbit, also with a larger semi-major axis, so very far from the star. And eventually, because the star that the planet is orbiting has a binary companion, so there is another star in the system. So that's another requirement of this mechanism, of the high eccentricity tidal migration mechanism, is that you have a star, you have a planet, and there has to be another body perturbing the orbit of the planet. In some cases, that extra companion could be a planet, but in this case it's a star. It's the binary star of the system. So what happens is that you have the star, this planet that started very far, roughly 10 astronomical units, and eventually the orbit of the planet undergoes coupling with the binary companion. So that's what happened to this planet. So the binary companion is starting perturbing the orbit of the planet. So the planet starts becoming very eccentric. The orbit of the planet becomes highly eccentric, and when it becomes highly eccentric, there is a quantity that decreases. The orbital angular momentum of the planet decreases. That's what we say, that the binary companion is extracting this angular momentum from the planet. And the consequence of that is that when the orbit starts becoming super eccentric, then you have these close passages of the planet through the periastron. So before you didn't have that, but once the orbit becomes super eccentric, then you have a planet that is passing really, really close to the star. So the star eventually starts extracting orbital energy, and with each cycle, with each pass of the planet through the periastron, more energy is extracted. And more and more and more. And eventually, the orbit of the planet shrinks, and you end up with a hot Jupiter.
That's Dr. Jaime Alvarado Montes from Macquarie University. Schwab says this shows that patterns and predictability do emerge when we view the progress of celestial bodies over astronomical timescales.
TESS is looking for change of the brightness in a star, and it finds planets by looking at stars and check, if a planet goes in front of the star, it will cast a shadow, and so the star goes dimmer for a short amount of time. And that's exactly what we saw for the particular star that the planet that we're talking about is orbiting. But in the initial discovery data, we only saw that once. So just, star got dimmer, star got brighter. we followed this up with a ground-based telescope with a spectrometer. I had built that spectrometer. The spectrometer is called NUIT. It's mounted on the Wind telescope in Arizona. It's a very precise instrument. And that spectrometer then looked at data that revealed, there's indeed a planet orbiting that star. And once we were sure that, it's probably a planet, we put more observing time behind it and started observing it regularly to really get to the parameters that planet is having. And once we did this, we realized that the planet is in a very unusual orbit. Normally, planets in our solar system, as you know, they all go around the sun basically in a circle, a little bit of an ellipse.
What we call the ecliptic.
Yeah, in the plane that we call the ecliptic, all in the same plane. They're all nice and their orbits are all nice and round. Now, what we saw when we got more data in on this planet, we saw that it's orbiting its star on a very, very elliptical orbit. So it comes very close, very fast, then it goes out, slows down, and comes back, goes very fast around the star, very close by, goes back out very far again. The objects in our solar system that do this are comets. And comets have this thing where they get very close to the sun on a very elliptical orbit and then they leave again. And we don't know planets in our solar system that do this. And so finding one that is on an orbit that's elliptical, as the one that we're here looking at, that comes so close to the star and then goes so far away again, it's very rare. And when it gets very close, it gets very hot, which is why we call this a hot Jupiter. And we call it a hot Jupiter because the size of the planet is about 5 times the size of Jupiter, the largest planet in our own solar system. And it's an intriguing discovery. There are only 2 planets of that mass in such an orbit ever discovered. This is the second one.
In our own solar system, we've seen something similar with Pluto as it orbits the sun at a highly elliptical and tilted angle, and that's being caused by Neptune. So that must have given you an idea that there was probably that this was a binary star system, and the second star or some other object was affecting the orbit of the hot Jupiter.
Yeah, so we would call it the hierarchical triplet system. Indeed, the host star has a companion star, and the companion star with its gravitational forces, with its tidal forces, is disrupting the orbit of that planet. You mentioned Pluto. Pluto sees similar things from the gravitational influence of the planets further in, Neptune and Uranus, but the effect on this hot Jupiter here is way more extreme. Pluto is on for a solar system point of view, elliptical orbit, but if you look at this, if you look at drawn maps, it looks a bit like an egg and not very, very elongated. But this one here is indeed very elongated. So the effect is much more extreme.
Yeah. Hence the common analogy.
And it comes in, and it comes in very close to the star as well and gets very hot, which Pluto, of course, doesn't do. But we think, or astronomers in general think, that those elliptical orbits are caused by gravitational forces of the other heavier bodies in the system, in this case, a second smaller star that also orbits the main star, and that these gravitational forces, these tidal forces, drove the planet to such an extreme orbit.
I like the headline, the 3-body problem. When I studied astronomy, the 3-body problem terrified me, as it does, I think, most postgrads. This was a good test of that 3-body problem because you had these 3 primary masses. One of them was being influenced by the other 2.
Yeah. I mean, the gravitational interplay between those in this really complex, weird orbit scenario is a complicated thing, and that is indeed the expertise of Chang'e, who recently has graduated. He was my student. He worked on this, so his expertise is looking at how orbits develop over time due to the gravitational pull of the bodies on each other. My expertise is actually building the instruments that we cover these with, but Chang'e has looked at the orbit and the orbital evolution. So we don't think that this particular planet will stay in this orbit for very long. We think that the orbit we see and the fact that, the gravitation from that second star in the system put the planet on an orbit that brings it very close to its star is one of the mechanisms, and this is scientifically the exciting part of that paper. We think this is the smoking gun for the mechanism that brings large planets close to the star. We have found these. In fact, the very first planet orbiting a main sequence solar type star is a hot Jupiter. It's a Jupiter-like planet, heavy planet with a gas atmosphere that orbits its star in a very close orbit. Now again, we don't see this in the solar system, and for a while we didn't understand how can you form these so close to the star. We actually don't think you can make these planets very close to their star. It's just too hot. It will evaporate the material off before you can form a planet that big. And so current thinking is those planets form far away from their star, and then something must happen that brings them closer. Call that orbital migration. And we think that we see here the mechanism that forces this, that the second star or a mechanism that forces this, the second star in the system push that planet on a weird orbit that brings it close to its host star, and tidal forces will make that orbit less and less and less eccentric over time, more and more and more round, and then will eventually end up in a close, tight orbit around the primary star of the system, being a hot Jupiter in a normal-looking orbit. And we see this while it's happening. And so this is exciting from a scientific standpoint, because here we can see, okay, how does the orbit actually look like while this is happening? And does it make sense from how we calculate these three-body problems and how we calculate the gravitational interaction between the bodies? Does that fit with what we think what's happening when those hot Jupiters are, in a way, being made?
That's Associate Professor Christian Schwab from Macquarie University. And this is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. Scientists have confirmed that 2024 was the world's first year with an average global temperature greater than 1.5 degrees Celsius above pre-industrial levels. The findings, reported in the journal Nature Climate Change, are based on two independent studies. The authors looked at averages over a 20 to 30-year period in order to allow for exceptionally hot years. They found that the climate data confirmed temperature averages have now passed long-term historical thresholds. In the first study, the authors found that it was likely that the planet is currently somewhere in the middle of its first 20 years of 1.5 degrees Celsius warming. The second study looked at month-to-month data. They say models show 12 consecutive months above climate thresholds indicate the threshold had already been reached. Keeping planetary temperatures below 1.5 degrees above pre-industrial levels was also the primary target of the Paris Climate Change Agreement. However, only 2 of the more than 100 nations which signed that agreement have actually provided a progress report, and Australia was not one of them. Meanwhile, Australia's Bureau of Meteorology has released its annual climate statement summarising weather and climate in 2024. The report found that last year was Australia's second hottest on land since records began back in 1910, and the hottest year on record globally. Sea surface temperatures in the Australian region as well as globally were also the warmest on record. Interestingly, it was also Australia's 8th wettest year on record, with overall rainfall 28% above the average. However, while rainfall was high in the north, partly due to tropical cyclones early in the year, it was much drier than usual in Victoria, parts of South Australia and some parts of the west, leading to reduced water storage levels in parts of the south. The report also found that Australia's total water storage volume was just under 73% at the end of 2024. That's similar to the previous year. And the report also showed that Australia was affected by low-intensity to severe heat waves during both early and late 2024. Scientists have found that the best way to get your dog to pay attention to something is to both point and stare at it at the same time. The authors tracked the gaze of 20 pet dogs wearing eye-tracking goggles, while their owners tried to get them to pay attention to a hidden food reward using 5 different methods. There was pointing, pointing plus gazing, gazing, fake throwing, and no action at all. A report in the Journal of the Proceedings of the Royal Society B found gestures shifted dogs' gazes towards the owner's hand, but when combined with a directed gaze, their attention then shifted towards the treat. The results show that a combination of pointing and staring was the most effective way to alert dogs to a hidden treat. Of course, accidentally dropping something, anything really, onto the kitchen floor works even better. Warnings about soothsayers and witches go back thousands of years to biblical times. The idea of witches as evil servants of Satan was ingrained in Judeo-Christian belief. The Malleus Maleficarum, usually translated as the Hammer of Witches, is the best-known treatise about witchcraft and often described as the ultimate compendium of literature on demonology in the 15th century. It was written by the German Catholic clergyman Heinrich Kramer in 1486. Years later, the Puritans took their biblical views to colonial America and the village of Salem. The Salem witch trials were the most famous flashpoint, culmination of religious extremism, xenophobia, social divides, and rivalries between settlers. but as Tim Mendham from Australian Skeptics points out, ties to witchcraft and the supernatural are common throughout the world.
Obviously, the big witch trials in the 1700s or something in Salem, Massachusetts. Became a hysteria there. Everyone was blaming everyone else. Everyone was accusing everyone else of being a witch, and therefore sort of people did get punished. The burning of witches in history is actually a lot less common than people often think it to be. In the period of James I of England, which was the early 1600s, there was a witch finder general and all this sort of stuff, and there was stories that coming out of so many witches executed.
There was a book, wasn't there, that helped you find witches and who is a witch and who.
Yeah, that's right. That's right. There was various books that were around at the time. But I mean, there were fewer people actually punished for being witches than the historical image would suggest. And the same is actually Salem. There was a few people involved, but it became a classic story of witchcraft. Then you get alternatives to witchcraft like voodoo and that sort of thing, which you obviously find in different areas. You find it in New Orleans with a lot of Cajun and Caribbean sort of religions and philosophies and those sort of places. And they have witchcraft and sticking pins in dolls and all that sort of stuff. So there are various places you can go to in America to find out about ancient or historical witchcraft and existing current witchcraft. Witchcraft there's white witches, of course, who supposedly do good, and there's the wise women or wise woman sort of concept of someone you go see for advice, whether it's herbal advice or whether it's a potion or something like that. The image of a witch is like someone who's associated with Satan and flying broomsticks and that sort of thing.
Wingardium Leviosa.
But the idea of a satanic witch is more story than reality. Well, it actually is story rather than reality, and the numbers a lot lower than you think of than you would be told in the movies. But you can travel any place in the world, you'll probably find examples of witchcraft. Australia has very few, as far as I know. Some of these people are just called witch because they're rather unpleasant, not because they do anything particularly magical. But it's one of the examples of things that are a nice myth, a nice sort of legend, a nice story, which is supported by media in one form or another to make it sound more exciting and more prevalent. In most cases, a witch, or as in a wise woman, was a pretty dull situation, just going for advice, hardly controversial.
She just was a woman who realised that if you had willow bark, you could relieve pain with that and things like that.
That's right. Yeah. And therefore, most witches are pretty mundane, if you can call them witches at all.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.